There is a kind of door that very few people have ever thought about, because it does not behave the way doors are supposed to behave. It opens only one way. Whatever sits behind it can move outward freely, without resistance. Light pours through, matter pours through, atoms and energy spilling out in a steady stream. But nothing crosses back in, not a single photon, not one grain of drifting dust. The door allows exit. It refuses entry completely. Physicists gave this object a simple name, borrowed from the bright flood of matter and radiation it was thought to release outward without end. A white hole. Tonight is not about a black hole, the familiar kind that pulls everything toward it and lets nothing leave. Tonight is about its apparent opposite, an idea that has sat inside the mathematics of gravity for more than a century, never once confirmed by a single telescope. You may remember a particular feeling from childhood, watching a film run backward, a shattered cup leaping up from the floor and reassembling itself in someone's hand, water climbing upward into a glass instead of falling out of it. That small unease, the sense of something moving the wrong direction, sits close to what physicists feel studying this particular kind of horizon. It should not behave the way it behaves, and yet, inside the equations, it does. We are going to spend some time with it tonight, slowly, without any urgency to resolve it before you drift off. No one has resolved it yet, not even the physicists who have spent entire careers trying. Let your shoulders settle into wherever you are resting. The story begins, as these things often do, with a far more familiar object, one that pulls everything inward rather than pushing it away. Most people who study physics for a living did not set out looking for an idea like this one. It found them instead, hidden inside calculations they were doing for an entirely different reason. That is often how the strangest ideas in science arrive. Not through a deliberate search, but as an uninvited guest, showing up in the middle of someone else's work. There is something oddly comforting in that. The universe does not wait to be asked before revealing something strange. It simply sits there, embedded quietly in the structure of things until someone happens to look closely enough. Think for a moment about the kind of curiosity a child carries before they learn to be embarrassed by it. A child asked once why a video could be played backward at all. Not why it looked strange, but why the machine allowed it in the first place. Why was reversal even possible, mechanically, if the world itself never seemed to run that direction? That question rarely gets answered fully, even for adults. We grow used to time moving one way without ever really settling the matter for ourselves. There is a quiet thread connecting that childhood question to tonight's subject. Physicists kept asking a version of it themselves, long after they had stopped being children. Not about a film reel, but about gravity itself, about the equations that describe how stars bend the fabric of space around them. If those equations can describe a black hole, a place that consumes light, swallowing it permanently behind a boundary, it cannot cross again, then somewhere in that same mathematics, a reversal seemed to be lurking, not because anyone wanted it there, because the symmetry of the equations seemed to demand it. Many of us carry a quiet expectation that the universe favors symmetry, day and night, hot and cold. A push somewhere implies a pull somewhere else. It is a comforting assumption, woven into how we make sense of nearly everything, from physics to ordinary life. The universe, though, has never promised to honor that comfort. Symmetry is something we notice. It is not something nature owes us. And so, for over 100 years, a small number of researchers have returned again and again to this particular idea, drawn back not by evidence, since there has never been any, but by the simple fact that the mathematics keeps refusing to let it go quietly. There is a particular kind of patience required for that, the patience of sitting with an unanswered question for an entire career, of returning to the same idea, decade after decade without resolution, simply because the question itself refuses to dissolve. It is the same patience, in a smaller and gentler form, that exists in anyone who has ever lain awake wondering about something without expecting an answer that night. Not anxious wondering, just quiet, open curiosity, turned towards something larger than the room you are resting in. That is the spirit this story asks of you tonight. Not urgency, not a need to resolve anything before you drift off. Just a willingness to sit with something unresolved, the way physicists themselves have sat with it for generations, and let the not knowing be enough for now. Before we go further into where this idea actually came from, it helps to understand the object it was born beside, the one this strange reversal supposedly mirrors, the one astronomers have actually seen. To understand why anyone would imagine an object that only lets things out, it helps to sit for a moment with the object it supposedly mirrors. The one we actually know is real. A black hole does not look like a hole. That word is misleading in almost every way. There is no tunnel hanging in space, no dark mouth swallowing stars. What exists instead is a region where the pull of gravity has grown so strong that escaping it would require moving faster than light itself. And nothing in this universe is permitted to do that. This idea traces back to Albert Einstein, who in 1915 proposed something that reshaped how every physicist after him would think about gravity. Gravity, he argued, was not a force reaching out from one object to grab another, the way Isaac Newton had described it centuries earlier. It was something closer to geometry. Ma bends the space around it. The more mass, the more severe the bending. Objects moving nearby simply follow the curves that have been carved into space itself. And what we experience as falling is really just motion along a slope none of us can see. The image often used is a heavy object resting on a stretched sheet of fabric, sinking into it, with smaller objects rolling toward the dip it creates. It is an imperfect comparison, but a useful one. Replace that object with something far heavier than any planet, far heavier than any ordinary star, and the curve in the fabric becomes a well with no visible bottom. Einstein's equations were notoriously difficult to solve. Even Einstein struggled with them. The breakthrough came from a German astronomer named Carl Schwarzschild, who worked out the first exact solution within months of the theory's publication. He did this while serving on the Eastern Front during the First World War, calculating in the margins of a conflict that would, within the year, cost him his life. Schwarzschild's solution described the space surrounding a perfectly spherical mass. Buried inside that solution was a peculiar number, a critical distance from the center of that mass, a boundary where the mathematics seemed to break apart entirely. Cross that boundary, and certain terms in the equations flipped side, behaving as though space and time themselves had traded places. Nobody quite knew what to make of it at first. Many assumed it was simply a flaw in the coordinates being used to describe the problem, the mathematical version of a fold in a map rather than a feature of the actual landscape. Decades passed before physicists agreed that the boundary was real and that it marked something we now call the event horizon. The event horizon is not a wall. It has no thickness, no texture, nothing a hand could touch. It is simply the line beyond which every possible path, in every possible direction, leads further inward. Outside that line, you could still turn a spacecraft around and fly home. Inside it, turning around no longer means anything. Forward has quietly become the only direction left. There is something worth sitting with in that. We tend to think of direction as a kind of freedom, the ability to choose where we go next. Near a black hole, that freedom narrows gradually, then disappears completely. Not because anything is physically blocking the way, but because the geometry itself has stopped offering an alternative. For most of the 20th century, black holes remained a mathematical possibility rather than an observed fact. Many physicists doubted nature would actually produce something this extreme. That changed slowly, through indirect evidence. Stars were found orbiting something invisible at tremendous speed. X-rays poured from regions where matter appeared to be falling into nothing. Eventually, in 2019, an international team of astronomers released the first image ever taken of a black hole's shadow, a dark circle ringed by glowing material captured at the center of a distant galaxy. That image mattered enormously, not because it told us anything new about the mathematics, but because it confirmed something theoretical had crossed over into something real. The universe had quietly been building these objects all along, and we were only now learning how to see them. White holes have never had that moment. No image, no shadow, no telescope pointed at the sky has ever produced anything that made an astronomer sit up and say, "There it is." And yet the idea has refused to disappear, tucked somewhere inside the same equations that gave us the event horizon in the first place. To understand why, we need to go back to that strange boundary Schwarzschild found and look at what later physicists discovered was hiding just beyond it. The Schwarzschild solution did not end at that boundary. It kept going. For decades, nobody noticed. The mathematics describing the region beyond the event horizon seemed to dissolve into nonsense, and most physicists assumed that was simply where the model broke down. The way a map runs out of detail past its edges. It took until the late 1950s and early 1960s for two researchers working independently to show that the equations were not actually breaking down at all. A mathematician named Martin Kruskal and separately a physicist named George Sekeres found a different way of describing the same space, using coordinates that did not collapse at the horizon the way the original ones had. What that new description revealed was strange enough that it took physicists years to fully accept it. The full Schwarzschild geometry, it turned out, did not contain one region. It contained four. One region was familiar. It described ordinary space, the kind we live in, far from any black hole. Another region was the black hole itself, the area inside the horizon where everything that crosses in continues falling toward the center, with no path leading back out. The third region was the surprising one. It looked almost exactly like the black hole region, except every arrow had been reversed, where the black hole's horizon allowed things to fall in but never escape. This region's horizon allowed things to escape but never fall in. Matter could only move outward through it into the ordinary universe, never the other way. This was the white hole, sitting quietly inside the same equation that had already given physicists the black hole, waiting to be noticed. The fourth region was stranger still. The mathematics suggested an entirely separate universe, connected to our own only through this geometry, never actually reachable, since anything attempting the crossing would need to move faster than light to make it through in time. A physicist named John Wheeler, who later coined the term black hole itself, helped popularize an image for this structure. He called it a bridge, connecting one region of space to another through the contorted geometry near the horizon. The idea had actually surfaced earlier, in 1935, when Einstein and a colleague named Nathan Rosen had explored a similar mathematical construction while trying to describe particles as smooth structures in space-time rather than as points. Their version came to be called the Einstein-Rosen Bridge, and it offered an almost irresistible picture. A black hole on one side, a white hole on the other, an entrance and an exit, joined by a passage running through the folded geometry between them. It is easy to see why the idea spread so quickly once people understood it. It solved an awkward problem rather elegantly. If a white hole continuously releases matter, where does that matter come from? A bridge answers the question cleanly. Nothing is being created. Something is simply arriving from somewhere else, the far side of the same structure, the black hole's collected matter finding its way back out through a different door entirely. It is a satisfying picture. The trouble is that satisfying pictures and physical reality do not always agree with each other. When physicists worked through the stability of this bridge more carefully, the news was not encouraging. The geometry connecting the two regions turned out to collapse almost the instant it formed, pinching itself shut faster than anything, even light, could possibly cross from one side to the other. The bridge existed in the mathematics. It simply never stayed open long enough to be useful for anything passing through it. That instability sits at the center of why white holes have remained theoretical for so long. A black hole has a formation story astronomers understand in detail. A massive star burns through its fuel. Gravity, no longer balanced by the outward pressure of fusion, wins. The star collapses inward faster and faster until an event horizon forms around what remains. Astronomers have watched stages of this process directly, through telescopes, across decades of observation. A white hole has no equivalent story. Nothing in known physics describes a natural process that would build one. The mathematics permits the geometry to exist as a solution. It offers no account of how such a thing would actually come into being, anywhere, ever. There is a version of this problem you may have already brushed against, without naming it. Most of us have, at some point, very late at night, wondered where a thought came from. Not what the thought was, but its origin, the place it must have existed before it surfaced. We rarely find a satisfying answer. The thought is simply there, fully formed. The way the matter from a white hole is simply there, fully in motion, the equation offering no account of its beginning. That is roughly where physicists found themselves with the white hole region of Kruskal's extended geometry. A structure that worked perfectly well on paper, mathematically self-consistent, internally coherent, and almost entirely disconnected from any plausible account of how the universe would actually produce one. Some researchers concluded the white hole region was simply an artifact, mathematically present but physically meaningless. The kind of solution equations sometimes generate without nature ever choosing to use it. Others were less willing to dismiss it so quickly. After all, the same equations had once predicted black holes themselves, decades before anyone observed one. Dismissing a mathematical prediction too early has its own history of going badly, so the idea persisted, not because anyone had found evidence for it, but because nobody had been able to rule it out completely either. And as physicists kept pulling on that thread through the decades that followed, it led them somewhere they had not expected, toward questions about time itself, and why the universe seems so reluctant to run in this particular direction at all. There is a question so ordinary that most of us stopped asking it somewhere around childhood. The moment grown-up explanations started feeling sufficient even when they weren't. Why does an ice cube melt but never refreeze on its own in a warm room? Why does spilled ink spread evenly through water but never gather itself back into one clean drop? Why does a glass shatter on a tile floor but never leap upward and reassemble in someone's open hand? None of those events are technically forbidden by the underlying laws of physics. That is the strange part. If you looked closely enough at the individual atoms involved, nothing in their basic rules says a shattered glass cannot reassemble itself. The atoms simply do not care which direction time happens to be moving, and yet it never happens. Not once, not anywhere, not in the entire observed history of the universe. The reason has a name, entropy. It gets described in textbooks as a measure of disorder, though that word undersells what is actually happening. Entropy is closer to a measure of probability, of how many different ways a system could be arranged and still look roughly the same from the outside. A deck of cards arranged in perfect order, ace through king, suit after suit, represent exactly one arrangement out of an almost incomprehensibly large number of possible arrangements. Shuffle it once, and the odds of landing back on that single-ordered sequence are so small they may as well be zero. Not impossible, simply, overwhelmingly unlikely. That is the entire secret behind why time seems to move in one direction. Not because some law explicitly forbids the reverse, because the reverse is staggeringly improbable, and the universe, given enough particles and enough time, always drifts toward whichever outcome there are more ways of reaching. Heat spreads out rather than concentrating. Gas fills a room rather than gathering into one corner. Stars burn outward into ever more diffuse light rather than pulling their energy back inward. Across nearly everything we observe, entropy increases. This single tendency, repeated at every scale, from a cooling cup of coffee to the slow expansion of galaxies, is what gives time its arrow. The reason yesterday feels different from tomorrow. There is a small, quiet thread connecting this to something. Almost everyone has felt at some point, usually late at night, usually while thinking about someone older. A grandmother once kept an hourglass on a windowsill, not because she needed it for anything in particular, just because she liked watching the sand fall. She would turn it over each morning. The same gesture repeated for decades, sand drifting downward in exactly the same direction every single time. It never once ran backward, no matter how many mornings she turned it. That small, repeated motion multiplied across every household that has ever kept a clock, every candle that has ever burned down rather than up, every grandparent who has ever told a child that time moves forward and forward only, carries the same physics buried inside Schwarzschild's equations. The sand falls one way because there are vastly more ways for grains to be scattered at the bottom than gathered neatly at the top. The universe simply follows the more probable path over and over, in every kitchen, on every windowsill, across every generation that has ever measured a day passing. This is where the trouble for white holes truly begins, deeper than questions about formation or evidence. A white hole, by its very description, behaves like a process running in reverse. Matter does not fall inward and settle into greater concentration the way matter, falling into a black hole, does. It moves outward, away from a center, expanding into less probable arrangements rather than more probable ones. Watching a black hole consume a cloud of gas looks, in a thermodynamic sense, exactly like what we expect. Disorder increasing, energy spreading toward where it can be more thoroughly scattered. The universe doing what it always does. Watching a white hole release that same gas outward looks like the reverse footage. Order spontaneously organizing itself into a coherent outward stream, the kind of event entropy almost never permits. That single observation troubled physicists for decades, in some ways more than any question about formation or detection ever did. A black hole fits naturally into the story the rest of the universe is already telling. A white hole tells the opposite story, quietly, at exactly the moment entropy insists no such story should be possible. The puzzle deepened further during the 1970s when two physicists, Jacob Bekenstein and Stephen Hawking, discovered something nobody had expected. Black holes were not thermodynamically simple objects after all. They carried entropy of their own, an enormous amount of it, proportional not to their volume, but to the surface area of their event horizon. This was a strange enough result on its own. It meant black holes behaved like genuine thermodynamic systems, with a temperature, with energy, with all the bookkeeping that ordinary hot or cold objects require. If a black hole carries entropy in this precise, measurable way, the question naturally followed for its theoretical counterpart. What entropy would a white hole carry? Would it decrease as matter streamed outward, violating the very principle that gives time its direction? Would it somehow increase, despite appearing to run in reverse? Nobody reached agreement. Different models produced different answers, and the disagreement itself became one more reason. Researchers hesitated to treat white holes as anything more than a mathematical curiosity. There is something worth resting on here before we move further. None of this means the universe forbids white holes outright, the way it forbids traveling faster than light. It means something gentler, and in some ways stranger. The universe simply seems to prefer the other direction, overwhelmingly, the way it prefers ice melting over ice forming, the way it prefers a shuffled deck over an ordered one. An idea can be mathematically permitted and still be, in practice, something the universe almost never chooses. That distinction sits at the very center of the white hole question, and it is one physicists return to again and again every time the subject resurfaces in a new context. It resurfaced unexpectedly when researchers began asking an even older question. Not how stars and galaxies behave today, but how the entire universe behaved at the very beginning, before any star had formed at all. There is a particular kind of stillness that comes from running a film backward far enough, past your own lifetime, past your grandparents, back through every century anyone has ever recorded, and continuing anyway, because the question never quite resolves itself. If galaxies are moving apart from each other now, drifting at a pace astronomers have measured with extraordinary precision, then running that motion backward means everything was once closer together. Closer and closer and closer still, until the entire observable universe, every star, every planet, every particle that would eventually become a person standing somewhere on a porch looking upward, occupied a space almost too small to imagine. Most of us picture the beginning of the universe as a kind of explosion, matter bursting outward into some pre-existing emptiness the way fireworks burst across a dark sky. That image, however vivid, is not quite right. There was no surrounding emptiness for anything to burst into. Space itself was smaller. Space itself expanded. The distance between any 2 points simply grew, the way the surface of a balloon stretches as air fills it, every point moving away from every other point, with no single center anyone could point to and call the origin. The closer physicists look backward toward that beginning, the hotter and denser everything becomes, until the equations, much like Schwarzschild's equations near the center of a black hole, simply stop working. Density rises towards something the mathematics describes as infinite, and infinity, in physics, is rarely treated as an answer. It is treated as a sign that the theory being used has reached the edge of what it can explain. This is the moment where an unexpected resemblance quietly enters the conversation. An extraordinarily dense, extraordinarily hot state, expanding outward, releasing matter and energy into space. Read. In isolation, without knowing where the description came from, it sounds remarkably like the very thing we have spent this entire evening discussing. Some physicists, over the decades, have allowed themselves to wonder aloud whether the early universe might share something genuine with the structure hidden inside Schwarzschild's geometry. Not that the universe was a white hole in any literal sense. The comparison is far looser than that, more of a shared shape than a shared identity. But the resemblance was striking enough that it kept resurfacing in serious research, again and again, never quite dismissed, never quite confirmed either. Consider, for a moment, an old wooden trunk passed down through a family for generations. Nobody alive remembers exactly how it was built, only that it has always been there, holding things, outlasting every person who has ever opened it. Each generation adds something new, removes something old, and the trunk itself simply continues, indifferent to whose hands are currently resting on its lid. Asking what came before the universe carries something of that same quality. The question feels natural, almost required, and yet nobody currently alive holds anything close to a confirmed answer. Some researchers have proposed that the very beginning of the universe might not have been a true singularity at all, the same way some now suspect the centers of black holes might not be either. Perhaps, instead, something deeper than classical gravity intervened, quantum effects becoming significant at scales smaller than anything our current instruments can probe directly, halting an infinite collapse before it could ever truly arrive, and reversing it into expansion instead. A bounce, rather than a beginning from nothing. If something like that occurred, the early universe would have behaved structurally, remarkably like the white hole sitting quietly inside Schwarzschild's old equations. Not proof, not confirmation, simply another place where the same strange shape kept appearing, uninvited, the way it always seems to. There is, however, a serious complication standing in the way of this comparison, and it returns us to the very thing we spent the last chapter sitting with. Entropy, the early universe, by every measurement physicists have managed to take, appears to have begun in an extraordinarily low entropy state, remarkably ordered, remarkably improbable, in exactly the sense a shuffled deck of cards is improbable when it happens to land back in perfect sequence. That fact alone remains one of the deepest unsolved puzzles in modern cosmology, entirely separate from any question about white holes. Why was the universe so ordered at the very beginning, when entropy, left to its own devices, should overwhelmingly favor disorder? Comparing the early universe to a white hole does not resolve that puzzle. In some ways, it deepens it further, since a white hole was already expected to behave in a thermodynamically unusual way on its own. Mainstream cosmology, for this reason, has generally kept its distance from treating the Big Bang as a literal white hole. The comparison remains useful mostly as a kind of conceptual scaffolding, a way of organizing an otherwise unanswerable question, rather than as an actual physical claim about how the universe began. And yet the resemblance refuses to fully disappear from the conversation, the way certain ideas do, lingering at the edges of serious physics without ever quite being invited fully inside. Perhaps that persistence says less about white holes themselves, and more about how little any of us currently understand regarding genuine beginnings, the kind with no prior moment standing behind them. It is worth sitting with that gently, rather than reaching for it. The earliest instant of everything remains even now, beyond the edge of what any equation can fully describe. That has not changed in the better part of a century, and it may not change for a long while yet. What has changed, more recently, is the kind of physics now being brought to bear on these old unfinished questions. Physics that doesn't describe gravity bending smoothly through empty space, but something stranger operating at scales far too small for any current telescope to ever directly observe. There is a particular kind of relief that comes from learning a problem might not be a dead end after all, simply a sign that you have not yet found the right tool to look at it properly. That relief sits at the center of one of the more recent developments in this story. The moment physicists began wondering whether the very thing that makes black holes so troubling, the singularity hiding at their center, might not be a true ending at all. Classical general relativity describes that center as a point of infinite density, where the equations simply stop offering answers. For most of the 20th century, physicists treated this as the final word, a genuine boundary where physics itself runs out. But infinities tend to make careful scientists uneasy, not because they are mathematically forbidden, but because nature, when examined closely enough, has a long history of avoiding them. An infinitely hot oven, an infinitely fast car, an infinitely full glass of water. These things appear in equations sometimes. They rarely appear in the actual world. This unease eventually led researchers toward a deeper question. What if general relativity alone is simply the wrong tool for describing the very center of a black hole? The way a map drawn for city streets becomes useless once you are standing in open ocean. What if something else, something quantum, takes over before the density ever truly reaches infinity? A handful of approaches to this problem, loop quantum gravity among the most developed, suggest that space itself may not be perfectly smooth at the smallest possible scales. Something closer to a fine grain, the way a photograph that looks seamless from across the room reveals individual flecks of color once you stand close enough. If space carries a structure like that, there may be a limit to how tightly it can ever be compressed, a floor beneath the falling, rather than an endless drop. And if collapse has a flaw, then perhaps it does not simply stop there. Perhaps, having nowhere further to compress, it rebounds, inward motion becoming outward motion. A black hole, quietly, over timescales almost too large to hold in the mind, becoming something that more closely resembles its theoretical opposite. The phrase researchers sometimes use for this is gentle, almost domestic, considering the violence of everything it is describing. A bounce. It is worth sitting with how strange this idea actually is, once you let it settle. A black hole, the very symbol of an irreversible ending, something nothing has ever been observed escaping, might not be an ending in the deepest sense at all. It might simply be the long, patient middle of something far slower than any of us could witness in a single lifetime. There is a complication here, and it involves time itself behaving the way it always seems to near these objects, unevenly. From the perspective of matter actually falling inward, a bounce of this kind might occur relatively quickly. But strong gravity stretches time for anyone watching from a distance. The deeper into a gravitational well something falls, the slower its clock appears to run from outside, and near the place where a bounce would theoretically occur, that stretching becomes extreme almost beyond description. What might feel from the inside like a single sharp turn, a reversal happening in some brief, almost ordinary span of time, could appear from the outside to stretch across trillions of years. longer, in some models, than every star currently burning in the sky, will have time to live and die before it happens. A black hole formed sometime in the deep past, sitting quietly above some other distant world tonight. Ordinary, in every way astronomers have ever measured one could in principle already be carrying this slow transformation inside it. Hidden behind a horizon, none of us will ever see past in time to watch it unfold. There is something almost unbearably patient about that. A process so slow that the very stars must finish their lives and grow cold before it reaches whatever comes next. This same idea has quietly wandered into one of the oldest unresolved arguments in modern physics, the question of what becomes of the things a black hole consumes. Quantum mechanics insists, with unusual firmness, that information is never truly destroyed, only ever rearranged, scrambled, perhaps beyond any practical hope of reading it again, but never erased completely from the universe's bookkeeping. Black holes have always seemed to threaten that principle, swallowing everything that falls past their horizon, and eventually, through the slow process Hawking discovered, evaporating away entirely. If a black hole can eventually become something that releases rather than holds, some researchers have wondered whether this offers a quiet way out of that old argument. Not lost, simply delayed, held somewhere unreachable for a span of time longer than anyone could comfortably imagine, before finally, eventually, finding its way back out into the universe it once left. Nobody has confirmed this happens. It remains one possibility sitting among several others, none of them settled, all of them still argued over by people who have devoted entire careers to a question with no agreed answer. Right now, as you are resting, somewhere out beyond every star visible from where you are lying, there may be a black hole, quietly carrying this slow process forward, indifferent to whether anyone is awake to wonder about it. It does not need an audience. It was never going to rush for one. There is something gently steadying in that if you let yourself rest inside it rather than reach for it. Whatever is happening out there, in that long, dark, unhurried interval between collapse and whatever comes after, it is not waiting on you to understand it tonight. It has time the way almost nothing else does. Perhaps that is the quiet shape of the question itself, not an ending demanding to be resolved, but a long, slow turning. Somewhere out past the reach of any clock we have ever built, there is a particular feeling that returns near the end of any long evening of thinking. When the questions that once felt urgent begin to soften into something quieter, less like puzzles and more like company. Think back to the grandmother and her hourglass on the windowsill, turning it each morning, sand falling the same direction it had fallen every single day before. She never once wondered whether the sand might rise instead. She simply trusted the motion, the way most of us trust gravity, without needing to understand the equations behind it. There is something worth noticing in that trust. An entire structure of physics, stretching from Schwarzschild's wartime calculations to questions about the birth of the universe itself, rests quietly underneath something as ordinary as sand falling through glass. The grandmother did not need any of it. The sand fell anyway. The day passed anyway. Time moved forward whether or not anyone in that kitchen had ever heard the word entropy. That is, in its own way, the most honest thing this entire evening has offered. Not an answer, but a reminder that the universe has been quietly keeping its own rules long before anyone thought to ask about them, and will likely keep them, long after every person currently wondering about white holes has been forgotten by name. The same child who once asked why a film could be played backward grew up, eventually, into someone capable of understanding Schwarzschild's geometry, Bekenstein, and Hawking's entropy calculations. The long, slow argument about whether collapse might someday reverse itself into something resembling release. None of that growing up made the original question disappear. It simply gave it better words. Perhaps that is what curiosity actually is across an entire lifetime. Not the search for a final answer, but the slow accumulation of better questions, each one carrying a little more of the universe's actual strangeness inside it than the one before. Somewhere, tonight, an object very far away may be quietly approaching the deepest part of itself. The place where collapse has nowhere left to go, where the old mathematics runs out, and something else, not yet fully understood, might be waiting to take over. Nobody currently alive will see what happens there. Nobody currently alive needs to. The not knowing does not need to feel like a gap. It can simply feel like an open door, left ajar for whoever happens to wonder about it next, 100 years from now, or 1,000, long after every grain of sand currently sitting in that hourglass has fallen through more times than anyone could count. The story does not close tonight. It was never going to. It simply rests here for a while, the way most long stories eventually do, somewhere comfortable, somewhere unfinished, somewhere it does not need to be anything more than exactly what it is.